Buongiorno a tutti. Good morning, everybody. Good morning, everybody. I hope you can see me. Not yet. Okay. Good morning, everybody. I am Giorgio Patrizio. I'm the president of INdAM, and on behalf of the Institute, the governing body of the Institute, and of the scientific committee that organized, together with Gioconda Moscariello, the vice president of the Institute, this INdAM Day, I'd like to welcome all of you to this 2021 INdAM Day. The Giornata INdAM has a long history now. The first edition was in 2004, and it is an important occasion for the Institute because of its twofold aims. The first one is a scientific one, of course, to have 4 distinguished speakers surveying a hot topic of current mathematical research. The second aim, which also is very important for a national institute like ours, is to meet and be together a local mathematical community. Well, this time, as it was last year, as you can see, the first aim of the INdAM Day is completely achieved. We have 4 fantastic speakers today. The second, for the second time in a row, unfortunately, cannot be realized this time. We still are experimenting difficulties, and our normal life is somehow, we are struggling with it. And for the second time, it was this INdAM Day was meant to be in La Sapienza, which, as you all know very well, has a special meaning for INdAM. And unfortunately, circumstances were not favorable. And also this time we had to step back to an online event. Now, it's not the right moment to discuss what is happening. We all are struggling with this situation, but nevertheless, just to send a message of hope, I'd like to confirm to all of you that the Institute is engaged in the serious effort to trying to come back to some sort of normality. And we are scheduling at the time, at this very moment, a couple of 2 or 3 Cortona meetings following the strict regulations, which we all try to support. And we are having, even this last part of the year, we are having events. And we are trying to make up a essentially normal schedule for next year. This is an important effort because somehow we are all coping in the best possible way with this very special situation we are living through. On the other hand, I think that most of us share my feelings. We are all tired of meeting using these means. And we do need some kind of normal way of meeting. And this is particularly true for the youngest part of our community. Young mathematicians are those who probably adjusted the best to these new online events and online communications because they are younger. On the other hand, they and all of us need to meet in presence again. And we owe this to our profession. And we will make an effort to try to of course, with the limitations and following the rules and so on and so forth, trying to have a normal schedule for as soon as possible. Now, just as a final word, regardless of this special way of meeting, again, we should enjoy this day. We have the program that has been set up by the scientific committee of the Giornata INdAM is great, and I really hope that we can share what is most precious for us, mathematics, and with this hope and in fact being sure of all this, I just stop here and I give the floor to Filippo Bracci, who is going to introduce our first speaker. Thank you very much.
Thank you, Giorgio, and good morning to everyone. So it is my pleasure to introduce Pietro Corvaia, the first speaker of our INdAM Day. So Pietro was born in 1967 in Padua, and he got his undergrad diploma at Scuola Normale Superiore in 1989 under the guide of Dvornicic. And he wrote a undergrad thesis about transcendental number. Then he got a fellowship from INdAM for 1 year in 89-90. And then he got finally his PhD in 1995 at Pierre and Marie Curie University with advisor Michael Wald-Smith and Michel Oran. In 1997, for 1 year, he was member of the Institute for Advanced Study and worked with Enrico Bombieri. Then in 2002, he came back to Italy and he got a position as associate professor in Udine. And finally, in 2005, he became full professor, which is in the University of Udine, which is the position that he is still holding. And I think that he's still the coordinator of the course in mathematics at Udine and the deputy director of the Scuola Superiore of University of Udine. From a scientific point of view, Pietro has been, work a lot, and up to now he has 57 publication with a great number of citation, and he published in journals like Invenciones, Acta Mathematica, Annals of Mathematics, Mathematician Annale, Crest Journal, American Journal of Mathematics, Journal European Mathematics, Transaction of American Mathematics Society, Advances in Mathematics, and so on and so forth. So really great journal and great work. His main subject of interest is Diophantine geometry, where he made several contributions, so I cannot tell all of them, and probably Pietro will speak about some of those. So I just here want to recall his work with Zanier on the integral points, and a paper where he solved a problem in p-adic geometry, a conjecture of Mahler. And then a recent paper where he was able to understand the maximal rank of the differential of the Betti map in relation with the Kodaira-Spencer map. The work of Pietro is not only, however, in the words of arithmetic geometry, but is very useful also in other fields, especially in Nevanlina theory, so and in several complex variables. And often, if you listen to such a talk, you can hear the name of Pietro, except that most of the time his last name is misspelled like Corvaja, but he's exactly Pietro, the one. And I know quite well now Pietro, because we spent together this time in more than 2 years in an Italian committee for scientific habilitation, and so I came to know him rather well, and I really enjoy to deal with him and to work with him. He's besides being a great mathematician, he's also a very nice and gentle person. So I'm very happy to introduce him. And so I leave the words to Pietro Corvaia, who's going to talk about analytic and rational sections of abelian schemes.
Okay, thank you very much, Filippo, for this generous presentation, which of course goes much beyond my merits. I thank the scientific committee of INdAM for inviting me to this prestigious event. And of course, I thank the local organizers in Università La Sapienza. I would like to be in Rome with everybody of you, but everyone knows the restrictions holding in Italy its presence. So let's try to share. I hope you're seeing my slides. So as announced, the title of my talk is Rational and Holomorphic Sections of Abelian Schemes. This title might discourage some listeners, but I'll try to be as elementary as I can and try to give an overview of different theories, from number theory and from complex and algebraic geometry. So I'll try to be comprehensible. I'll try to give a talk for everybody, knowing that the audience is very vast. So let's try to give a pandemic talk in the etymological sense of a talk for all the people. The main aim of the talk is showing the links between 3 different domains of mathematics. So number theory, which is my main motivation, and especially I'll be interested in Diophantine geometry, which concerns the distribution of rational and integral points on algebraic varieties. Then algebraic geometry, this is also a very large domain. We shall be interested in morphisms between algebraic varieties and most precisely of sections of fibrations, and complex analytic geometry, and especially in the theory of entire curves on complex algebraic varieties. More precisely, the topics will be elliptic curves over Q, over the rationals, and the corresponding theory of heights. And then we shall consider elliptic schemes, or in another language, the language of classical algebraic geometry, elliptic surfaces, which are algebraic surfaces fibered in curves of genus 1. Then abelian schemes, which is a higher dimensional generalization of the theory of elliptic schemes. So algebraic families of abelian varieties, where we shall be interested in describing the sections. And then we shall touch hyperbolicity questions. So problems originated from Picard theorems and sometimes studied via the so-called Neyman-Lingner theory. And finally, we shall study the theory of a height for sections of abelian or elliptic schemes, which is the natural analog of the theory of heights for rational points. Most of the results will, and the theory presented here is classical, but I shall also show some new results, which have all been obtained in collaboration with the people listed here: Yves André, Julian De Meyer, who is a PhD student of Zanner in Scuola Normale, David Massa, Tunjiro Noguchi, and especially Umberto Zanner. So let's start from the theory of elliptic curves over Q. An elliptic curve is an irreducible smooth projective curve with a group structure. And it turns out that it must have genus 1. I'd like to pause a moment to explain the importance of elliptic curves in number theory, in Diophantine geometry. A famous theorem of Faltings states that rational points on any algebraic curve of genus at least 2 are finite in number. And concerning curves of genus 0, there are two cases. Either such a curve has no rational points at all. Just think of a conic, a smooth conic without a real point. In particular, it has no rational points. And in the case there are no rational points, there is an effective procedure to prove this fact. Or if there is at least one point, then the curve is isomorphic over Q to the line, and so the rational points are very well understood. So in one case, they are genus 0 case, there are infinitely many and easy to parameterize. Genus 2 or more, there are finite numbers, and elliptic curves are those in between. And that's why the arithmetic theory of elliptic curves is particularly interesting. And complex analytically, an elliptic curve is a compact torus, a quotient of the complex number plane by a two-dimensional lattice. So topologically, the complex point of an elliptic curve is the product of two circles. And also, if you think at the theory of Riemann surfaces, you see that elliptic curves are in between from one side the Riemann sphere, and from the other side the hyperbolic compact Riemann surfaces, which are those of genus at least 2. And a classical theorem, which is the complex analytic analog of Falken's theorem, and which was proved much earlier and by much more elementary means, states that every holomorphic map from C to a genus at least 2 Riemann surface is constant, while it's clear that there are holomorphic, non-constant holomorphic maps to a complex torus. Simply take a function to C and then project modulo lambda. Now, an elliptic curve always admits a plain affine model as a cubic form. You can always write that equation y squared equals a polynomial of degree 3 in cube, rational coefficients, with distinct complex roots. And I said that the elliptic curve is a smooth projective curve, and I write down an affine equation. It will be always meant that to the affine points, the solutions of the equations you're viewing, one must always add the points at infinity. In this case, there is just one point at infinity, which is the common point to every vertical line in the plane. And this point will be taken as the origin for the group law. And this group law, which complex analytically comes from the addition on C, admits a simple description in terms of the cubic model of the algebraic equations. This is a picture of the real point of an elliptic of a cubic curve. You see that the point at infinity will be the vertical point, because if you move in the one or the other branch, the slope will increase to infinity, so that the completion, the point to add, will be the point at infinity on the vertical line. Now take 2 points, Q1, Q2. Their sum is obtained in this way. You join them, you obtain a third point, and then you join R with the point at infinity, which means in this case you draw the vertical line through R, and you obtain the point minus R, which will be, by definition, the sum of Q1 and Q2. And this is the group law corresponding to uniformization by C. And it's clear that if the equation is defined over the field of rational numbers, and the starting 2 points Q1, Q2 have rational coordinates, the new points R and minus R will also have rational coordinates. So this is a method already shown by Fermat in the 17th century to obtain new solutions to the original equations over Q, starting from previously obtained ones. Now, famous theorem by Mordell states that the set of rational points is a finitely generated abelian group. So in geometric terms, you can always find a finite set of points on the elliptic curve, such that all the other rational points are obtained using the trick which I explained in the previous picture. And this theorem was generalized by André Weil to arbitrary abelian varieties, which means higher dimensional projective varieties with a group structure, and to number fields instead of just the rational number field. Let's see an example. This is Fermat Cubic. Here x, y, z are to be interpreted as homogeneous coordinates in the plane. So so one equation, 3 homogeneous variables defines a curve and not a surface. And if you choose one point as the origin, say the points at infinity, the rational point at infinity 1, -1, 0, then by the special case of Fermat's theorem, which was proved by Euler, the other rational points are just 1, 0, 1 and 0, 1, 1. And the group law states that the points are all of order 3, and twice A equals B, twice B equals A. Let's see another example. And in this case, we have a point of infinite order, -2, 8, and a torsion subgroup consisting of 4 points. Again, we take the point at infinity as the origin, and infinitely many other points are obtained by doubling, tripling, and so on P. For instance, here I wrote twice P, and well, I didn't calculate 3 times P, but 4 times P, you see, is a huge number. Now, the theory of heights on elliptic curves. First, let us define the height of a rational number written in a reduced fraction as the maximum of numerator and denominator. And the height of a point in the plane can be defined, for instance, by taking the maximum of the heights of the coordinates. And a fundamental theorem on the theory of heights on elliptic curves states that if you take a rational point on an elliptic curve, then you multiply this point by n, according to the group law on the elliptic curve, and the limit that you see exists and is finite. Note that the logarithm of the height of a point is, roughly speaking, up to a constant, is the number of digits you need to write down explicitly that point. For instance, for the point for P, you need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, and then, well, calculate how many. You need many more digits than to write down P, which is written with just 2 digits, or twice P, which just needs 6 digits. And Mordell Theorem states that the complexity, the arithmetic complexity of the coordinates of NP grows as n squared. And also this limit vanishes clearly if P is a torsion point, because in that case, NP has only finitely many possibilities, while the denominator tends to infinity. And a deep fact is that it vanishes only if P is a torsion point. And if we denote by H hat the upper limit, then we obtain function of P, which is a positive definite quadratic form for the group structure on the rational points. And also this so-called normalized height differs by the logarithmic height of P by a bounded function. Now, let's come to elliptic schemes. An elliptic scheme is an algebraic family of elliptic curves, depending algebraically on a parameter. So formally, it is a morphism from a quasi-projective algebraic surface E to an affine algebraic curve B, such that each fiber is an elliptic curve. The basic example, called the Legendre scheme, is provided by an equation in 3 variables, so defining a surface. If you view T as a parameter, then for each given T, its equation of the form y squared equals a polynomial of degree 3 in X. And if you move T in C minus 0, 1, the corresponding curve will be smooth and it will be an elliptic curve, while for the special values of T equals 0 or 1, we obtain a singular curve. So they are called points of bad reduction. One can view also an elliptic scheme as a single elliptic curve, which is defined over the field of rational functions. So let's come back to that equation. You can think that the field of constant is the field of rational functions on the variable T, and this is one equation in 2 unknowns, so the equation of a curve, not a curve over C or over Q, but over C of T. So in viewing elliptic scheme in this sense, a rational point will be a point in the plane whose coordinates are not rational nor complex numbers, but are rational functions, x of t, y of t. And geometrically, they correspond to sections. Sections from the base to the total space E, which is, by definition of section, is a right inverse of the projection. So take a generic equation, y squared equals a polynomial in x depending on the parameter. Then take a solution x of t, y of t of the above equation. We obtain a morphism sending t to the triple x of t, y of t, t, which is a point on the surface defined by the displayed equation. So, for instance, for the Legendre scheme, a section can be defined by taking x of t equal t and y identically zeros. Clearly, if x is t, the right-hand side vanishes. And so you obtain a section t0 t. And in this case, the group of sections only contain torsion sections, namely the zero sections, the above section, and two other sections obtained by setting x equals 0 or x equals 1 and y always 0. And this is a group of order 4. It consists of the two torsions. We shall be interested in elliptic schemes which are not isotrivial, in the sense that the fibers are non-isomorphic ellipticals, so they are not all isomorphic to a single elliptical. Now we have stated Mordell theorem over function fields. If the elliptic scheme is not isotrivial, its group of rational sections is finitely generated. So it's exactly the analog of Mordell theorem over Q. Now, the height of a section, the analog of the log h defined for rational points, will be the maximum of the degree of x and degree of y. And again, we have a kind of Néron-Tate theorem leading to the definition of the normalized height. It's defined exactly in the same way. Start from the naive height of a point, multiply this point by n for every n, and divide by n squared. Now let's come to complex analysis. A holomorphic section of an elliptic scheme is simply defined as a holomorphic map from B to E, sending each point of B to some point of its fiber. And if we work with an algebraic model, y squared equals polynomial in X, then a holomorphic section is a solution x of t, y of t, where x and y are possibly transcendental analytic functions. Here we note that if B is an algebraic curve, which we are assuming, necessarily the map pi is a morphism of algebraic varieties. This is due to the hyperbolicity of B. If the scheme is not isotrivial, B must be a hyperbolic curve, and a Picard-like theorem proves that that the map pi must be a morphism of algebraic varieties. In other words, there do not exist transcendental elliptic families of an algebraic base. So we shall always consider algebraic family of elliptic curves, but we shall be interested in holomorphic sections. And here we have a rationality criterion, which is a highly non-trivial result. This has been obtained in collaboration with Noguchi and Zanner. And if we take a non-isotrivial elliptic scheme, then we take a holomorphic section And we prove that sigma is rational if and only if it intersects the zero section at only finitely many points. In particular, if sigma omits completely the zero section, then it is rational. The proof makes use of a recent result of Yamanoi in the van linear theory, which can be viewed as a second main theorem with moving targets and with truncated counting function. And it is the analog of a result theory of Riemann surfaces that if you take, the second part of the theorem is the analog of what I'm going to say, that B be in a affine algebraic curve, so a compact Riemann surfaces minus a finite set, and E an elliptic curve and P one of its points, then have a holomorphic map omitting P is rational. For instance, there are no non-surjective holomorphic maps. Here it's not, the sentence is not complete. Holomorphic maps from C to E. Now let's consider the problem of logarithms of sections. Take an elliptic scheme. Each fiber is isomorphic to the quotient of C by a lattice, which moves with T. The uniformizing space C can be identified with the relative tangent space to ET. This comes from the classical theory of the groups. And the union of these copies of C forms a holomorphic line bundle over B, which is necessarily trivial. Recall that B is an open Riemann surface. It's an affine algebraic curve. So we can identify the total space of this line bundle with the product obtaining the following diagram. The arrow from B cross C to E is a topological covering map. And the one from the arrow from E to B is the vibration, the starting vibration. And now a logarithm of a section is a lifting of sigma to B cross C. So we have a section from B to E, a logarithm that meets a logarithm if it admits a lift to the covering space. And locally, a logarithm always exists, and rational sections never admit globally defined logarithms, while holomorphic sections might admit logarithms. And it turns out that the quotient of holomorphic sections modulo those sections admitting a logarithm is a finitely generated abelian group. And this finitely generated group only depends on the topology of the fiber bundle of E to B. Sorry for these typos. Now, given an elliptic scheme and a simply connected open set, one can define a basis for the period lattice, namely two holomorphic sections, two holomorphic functions, such that the lattice over each point T is generated by the values of these functions. And given a section, one can define locally its logarithm and also express this logarithm as a linear combination with real coefficients of omega 1, omega 2. So write the logarithm of sigma as a real linear combination of the periods. And this map is called the Betti map associated to the section. And the integral values of beta correspond to the vanishing value of sigma. So it corresponds to the points where sigma equals the the neutral element of the elliptic curve, while rational values correspond to torsion values of sigma. Famous theorem of Manning's states that unless the section is torsion, the Betti map is not constant. This was generalized to arbitrary abelian scheme and arbitrary basis. Under suitable hypothesis, the conclusion states that the Betti map is submersive. This is a result obtained in collaboration with Yves André and Umberto Zanner. The functions beta 1, beta 2 can be defined locally on the total space on the elliptic scheme independently on the section. So a point in the total space is in particular a point on one fiber, so on one elliptic curve. It admits a logarithm, and this logarithm can be expressed in terms of the periods. So changing coordinates affects beta by, first of all, addition of integers, which correspond to periods, because logarithms are defined up to periods, and also changing a basis of the period produces the effect of multiplying beta on the left by matrix with integral coefficients. A matrix with integral coefficients is necessarily locally constant. Then it turns out that the differential two forms, d beta 1 wedge d beta 2, is well defined, does not depend on the coordinates. And it satisfies this property. It is a closed 1-1 form on the total space. It is an eigenvector for the multiplication by n, and precisely you see multiplying by n changes omega by a factor n square, which is exactly the factor appearing in the theory of heights of rational points on elliptic curves. And its integral on each fiber equals 1, so it's the volume form on each fiber. And here we have this theorem, which is an integral height formula obtained in collaboration with De Meyer, Masser, and Zanner. That given irrational sections, the normalized height can be computed as the integral over the base of the pullback of the sections. And it follows that the height can also be computed by counting the number of torsion values of sigma. And for each n, look for the number of points where sigma takes n torsion values and divide by n squared. Transcendental holomorphic sections, the above integral never converges. And then we define an analog of the characteristic function of Nevan linear theory. So we compactify the affine curve, we choose an exhaustion. So we approximate B by Riemann surface denoted by B of R. So basically we remove a disk of radius 1 over R over on the points centered on the points at infinity of B, so that the limit for R tending to infinity of B of R is the full Riemann surface B. And then we define the characteristic function associated to sigma as the integral that you see there. This is a formal analog of Alford-Shimizu characteristic functions in Nevan linear theory. And we prove this theorem together with Noguchi and Zanner that the holomorphic section is rational if and only if its characteristic function is a big over log R. This is again the analog of a theorem of Nevan-Lindner for entire functions. Now let us consider abelian schemes. An abelian variety is a higher dimensional irreducible projective variety with a group structure. Complex analytically, it's again the quotient of Cn by a lattice. And topologically, it is the Lie group R to 2Bn modulo Z to 2Bn. An abelian scheme is an algebraic family of abelian varieties varying algebraically over an algebraic base. Let's think of an algebraic curve. And here, unlike the case of elliptic schemes, there do exist abelian schemes over a projective base. So there are abelian schemes with no bad reduction. This is due to the fact that the moduli space of abelian varieties given polarization can contain also complete curves. Let's state two classical results in the constant case. The constant case means a single abelian variety, so not an algebraic family. So take an abelian variety of a complex number field and a holomorphic map from C to A. And the risky closure is a translate of an abelian subvariety. Another theorem, if you take an ample divisor and think of an ample divisor as a hypersurface obtained as a hyperplane section in an embedding of A into a projective space. So an ample divisor, and every holomorphic map omitting this ample divisor is constant. This results in complex analysis, admit an analog in number theory, which have been proved by Faltings in the 90s. The first result is that an algebraic subvariety of an abelian variety defined over a number field, let's say over Q, then the risky closure of the set of its rational points is a finite union of translates of abelian subvarieties. And the analog of the second theorem is that if you take an affine variety whose projective closure is an abelian variety, then the set of integral points is finite. Now we considered in the work with Noguchi and Zanner the analog of these results in the relative situation, meaning for a non-constant abelian scheme. So let's consider this problem. Take a holomorphic section of an abelian scheme, then prove that the risky closure of its image consists of a translate of an abelian subscheme. This is still an open problem. A second problem, a holomorphic section omitting a relative ample divisor. This means a divisor in the total space such that its intersection with a generic fiber is an ample divisor. And then sigma is rational. We have obtained a big Picard-like result. So take consider the puncture disk delta star and recall the classical big Picard theorem that if a holomorphic function admits an essential singularity at the origin, then it omits at most one complex value. Equivalently, if the holomorphic functions omit zero, so it's a function to C star, and it has an essential singularity at the origin, then it is surjective. Now imagine to replace C star with an abelian variety. C star finally is itself an algebraic group, so, but it is a fine algebraic group. Replace it with a projective algebraic group, so with an abelian varieties, and more generally with a smooth family of abelian varieties. So this means a family without Bell reduction over delta, and take a relatively ample divisor and take a holomorphic section. We have proved this theorem. If sigma does not extend to a section at the origin, so this is the analog of having an essential singularity, then its image must touch infinitely often the divisor D, or the other way around. If it omits D, then it extends to the origin. Now we have another result. This time we start from a projective algebraic curve and an abelian scheme over the whole curve, so without bed reduction. As I said, there do exist abelian schemes with no bed reduction. Take a relatively ample divisor, and we prove this theorem. If you take a holomorphic section with a risky dense image, then the intersection with the ample divisor is infinite. Here we insist that the section is defined on an open subset of the compact Riemann surface of the algebraic curve, but the abelian scheme must be well defined over every point of the base. So this answers one of the two open problems which I stated, up to the fact that we really need that the abelian scheme be defined at every point of P. Well, I think that I can stop here, and thank you very much for your kind attention.
Thank you very much, Pietro, for your very interesting talk. So maybe I should have said this before, but I tell now. Please write on the YouTube chat if you have any question. And since there is some delay between our actual video and YouTube, maybe I can start to ask to the people here of the scientific committee if they have questions. Otherwise, I have a couple of maybe curiosity for Pietro. So the first thing I would like to know is you talked about the growth of characteristic function, and you proved that it goes like log of R if and only if the holomorphic section sigma is rational at a certain point, right? So I was curious about the bound. I mean, what is known about the possible growth of this characteristic function? If there are other extremal value and other consequences, or you have conjecture, or maybe nothing?
So I have a bit problem with the audio. Can you repeat louder, please? I don't know how to increase the audio. Sorry for that.
No problem. Well, this is the nice part of the online stuff. So I was asking you showed at a certain point that the growth of the characteristic function, if the growth of the characteristic function goes like log of R, this is the case if and only if the associated holomorphic section sigma is rational.
Yes.
So I'm asking whether you can say something else, or there are any conjecture for a different behavior of growth of the characteristic function.
Well, thank you. Now I understand. Actually, the characteristic functions can be as large as one wants. So there are no upper bounds. It can tend to infinity arbitrarily fast. And this can be viewed, for instance, from the fact that there do exist holomorphic sections admitting a logarithm. A holomorphic section admitting a logarithm basically correspond to a function from B to C, from the base to the complex field. And then you can, if you can construct a one non-constant function to C, we can construct as many as you want with arbitrary high growth. I don't know exactly about the intermediate possibility between log R and R, for instance. This I don't know, but so one can try to improve the rationality criterion, replacing log R by something going faster, maybe. This I don't know.
Mm-hmm. Thank you. And then the second question was about this theorem that you mentioned, when you have an ample divisor of an abelian subvariety, then if you have holomorphic mappings whose image is in the complement, then it is constant. So this reminds to me the so-called Kobayashi conjecture that you probably heard of in several complex variables, that, for instance, if you have P2 and you remove a generic algebraic curve with sufficiently high degree, then the complementary is Kobayashi hyperbolic, and in particular there are no non-constant holomorphic mapping on the complement of this. And as far as I know, there are some proof of this conjecture which are done by Desmailly, who used this method of bundles of jet bundles and so on and so forth. So I'm just curious if you see any relation between the two, and how maybe whether your method can be adapted, or I don't know, in this case.
Yes, thank you. The parallel conjecture is by Vojta in number theory and by Green-Griffiths in complex analysis, linking hyperbolicity with the canonical divisor. So according to this conjecture, if you take a smooth projective algebraic variety, remove a hypersurface, let's call it D, such that the sum D plus K, where K is a canonical divisor, is a big divisor, then the complement should be, in a sense, weakly hyperbolic. Complex analytically, it means that this complement should not admit Zariski dense entire curves. And arithmetically, if everything is defined over a number field, it should be true, this is a conjecture by Vojta, that the set of rational integral points on the complement is not Zariski dense. So take, for instance, the case of the projective plane. Its canonical divisor is in the class of -3 lines. So if you remove a curve of degree 4 and or more, the complement should have this property. So there might exist entire holomorphic curves to the complement, but they should be contained in algebraic curves. For instance, if you remove a smooth quartic from the plane, it is well known that smooth quartics admit bitangents, and the bitangent is a copy of P1 touching the curves at only 2 points. So it's C star, and then there do exist holomorphic maps from C to C star. So there do exist entire curves, but their image are algebraic curves. If you remove a sufficiently generic algebraic curve of degree 5, it should be true that the complement is really hyperbolic in the strong sense, in the sense of Brody, and maybe also in the sense of Kobayashi, but this is still open. There are partial results for higher degree, but again, under the conditions of very genericity. So not for every smooth algebraic curve. And if you think of abelian varieties, the canonical divisor is 0. So according to Voiter and Green-Griffiths conjectures, it should be sufficient to remove one single ample divisor of any degree to obtain hyperbolicity. And this is a theorem of Faltings in number theory, and Bloch-Rouchai and so on in Nevanlinna theory. And in both contexts, there also do exist a quantitative version of this theorem. In the complex analytic case, it's a so-called second main theorem, proved by Noguchi and his school, giving a bound for the so-called proximity function to the divisor removed from an abelian variety.
Okay, thank you very much for the clarification. So, are there other questions? So I don't see any question on the YouTube chat. Okay, so if not the case, I thank Pietro again for this wonderful seminar. And we resume as on the program at 11:30 with the next speaker. Thank you.